As I said a little bit earlier, if you weren't here, my name's Eileen Donovan-Wright. I'm the Associate Dean of Research in the Faculty of Medicine, and I'm really pleased to be here. I'm really pleased that everyone made it. We heard there was a traffic accident, but there's a real joy in getting together at these breakthrough breakfasts to celebrate some of our incredible health research. And it's good to remember that this is a team sport, and it's happening at Dalhousie and with partners, and it's happening now. So it's an exciting time for us. Before we begin our day, I really want to acknowledge that Dalhousie University operates in the unceded territories of the Mi'kmaq, Wolastoqey, and Mbezgo-Dumaquati peoples. These sovereign nations hold inherent rights as the original peoples of the lands, and we each carry collective obligations under the Peace and Friendship Treaties, Section 35 of the Constitutional Act, 1982. And that act recognizes and affirms Aboriginal and treaty rights in Canada. So, designed to celebrate groundbreaking research and medical innovation, each event in our Breakthrough Breakfast series showcases an area of medical research discovery, featuring Dalhousie research at the forefront of their fields. Today, we'll be showcasing 4 Dalhousie medicine researchers who are innovating and leading ways in genetics and genomics research. Genetics and genomics research are making significant strides in addressing real-world health challenges, impacting health through personalized medicine, more informed disease prediction and prevention, improved cancer treatments, and genetic screening. These advancements are just a few examples of how genetics and genomics research are transforming healthcare and improving patient outcomes. I'd like to extend our sincere gratitude to our sponsors and partners who make events like this possible. Our gold sponsor, Shanex, a family-owned organization with a vision of leading the way to better living. Shanex has been a gold sponsor of our Breakthrough Breakfast series throughout the last year and makes these public presentations possible. So thank you, Shanex. Our silver sponsor is Dalhousie's Department of Medicine, dedicated to building a healthier tomorrow together through our commitment to excellence in quality care, research, and education. Join me in a round of applause for both of our sponsors. So we've brought you out here at 7:30 in the morning. Please continue to enjoy your breakfast as we begin our program. I think they'll be coming around with more coffee, and if you look desperate, I'm sure they'll come even faster to your table. I'd like to invite Dr. David Anderson now, Dean of Medicine in Dalhousie, to stage to bring greetings. Just before he jumps in, because he's always ready to jump in, before he joins us, I'd like to note that this is a particularly special Breakthrough Breakfast, as it marks Dr. David Anderson's final event in his role of Dean before the conclusion of his second term this June. But please join me in welcoming Dr. Anderson to the stage.
Good morning, everyone. Really a pleasure to be with you here this morning. Sometimes when you look out the window, you feel you've got a hotel right beside you with these incredible cruise ships that come to town. But it is great to be here, and thank you for coming for our Dalhousie Faculty of Medicine Breakthrough Breakfast, The Promise of Genetics and Genomics. At Dalhousie, we're proud to bring people together who are curious, committed, and passionate about making a difference, and today's conversation is a powerful example of that. We're here to explore one of the most exciting and transformative areas of modern medicine, genetics and genomics. Not long ago, the ability to read and interpret the human genome was theoretical. Today, it's redefining how we understand disease, how we diagnose it, and how we treat it. Genetics and genomics are moving us beyond a one-size-fits-all model and approach to care towards a future where treatment is tailored to each individual. A future where diseases can be detected earlier, therapies are more precise, and outcomes are significantly improved. This future isn't abstract. It's already beginning to take shape. Right here at Dalhousie, in collaboration with partners at the IWK and Nova Scotia Health, our research are advancing discoveries that are changing lives. They're uncovering the genetic causes of rare diseases, developing new approaches to cancer care, improving our responses to infectious diseases, and using powerful tools like artificial intelligence to make sense of complex biologic data. Importantly, this work is happening in and for Atlantic Canada, addressing the unique needs of our region, including our higher rates of chronic disease and barriers to accessing specialized care. Today, you'll hear directly from some of the researchers leading this work. They will share their discoveries and discuss the possibilities that lie ahead. I hope you'll find their insights as inspiring as we do. Thank you again for being here and for your interest in supporting research that has the potential to transform the health of our communities and far beyond. Thank you very much.
Thank you so much, Dean Anderson. Now, without further delay, we have an esteemed lineup of researchers who will share their latest insights and research findings in the exciting area of genetics and genomics. There's four of them: Dr. Chris McMaster, Dr. Luke Chen, Dr. Manuel Matison, and Dr. Sonia Stanievich. First up, please join me in welcoming Dr. Chris McMaster to the stage to share his insights on identifying and repairing genes to improve outcomes for those born with rare genetic diseases. Dr. Chris McMaster is a professor of pharmacology at Dalhousie's Faculty of Medicine and director of the Cheminformatics Drug Discovery Lab. He's also, in his spare time, the scientific director of the CIHR Institute of Genetics for another year or so. He is a leading researcher in genetics, biochemistry, and cell biology, and has been involved in various leadership positions in academia and in the private sector, focusing on translating research into better patient care for genetic and infectious diseases. His work includes using genomics to better predict health and disease, working towards the use of genomics in learning health systems, and incorporating Indigenous values into genomics research. Dr. McMaster has also been instrumental in creating a pan-Canadian pediatric rare disease clinical trials and treatment network. That is not an easy thing to do, and that's been a labor of love over several decades. And that network together is finding pathways to bring gene therapies to first-in-human clinical trials for genetic diseases, and you can imagine that that changes lives for the entire duration of their life. So please help me welcome Dr. McMaster to the stage.
Good morning, everybody, and thank you very much for getting up this early to listen to what we've got to say. I hope you find it worth the time. We're going to talk a little bit about inherited diseases, and I'm going to talk mostly about inherited diseases in children. These are things that actually really fall under the radar when it comes to the medical system. Yeah, unfortunately, they shouldn't. In Canada and around the world, 1 in every 15 babies is actually born with an inherited disease. What does that mean? Well, each of us has 21,000 genes. When you get an inherited disease, one of these genes doesn't work, just one. The other 20,999 do their job. But when that one gene doesn't work, you end up with an inherited disease, and there's several thousand of these inherited diseases. But when you look at these inherited diseases en masse, it's 1 in 15 babies born. It is the #1 reason kids end up in hospital in pediatrics. Unfortunately, 95% have no treatment whatsoever. They were very intractable until recently. Sadly, 1/3 of these children will not see their 5th birthday. Over half of these kids will not reach adulthood, which is why when you're wandering around looking in this room, where's the inherited disease patients? Well, they passed away at a very young age. I will say, I wasn't going to go here, but this includes my daughter. She passed away last year at the age of 29 from an inherited disease because couldn't do anything about it, but we're trying to change this for kids in the future. So there is hope, and the hope is gene therapies. Gene therapies are now in the clinic, and they work. There's only 11 approved in the world thus far, but it's a technology that works well, and we're looking to have Dalhousie universities be leaders in. It's very simple in principle. You've got one gene that doesn't work. We've now found, using some schmancy genetics tech, that you can actually take the one gene that doesn't work and put a normal copy back into the child, so that they now have a working copy of the gene, and it's essentially a cure. The nice thing about it is, the good news is it's thought to be permanent. You give a gene therapy once, you're cured for life. Isn't that great? Bad news, the average cost right now is $4 million per gene therapy per child. It's a big number. Part of this reason is all treatments have arisen from the private sector, pharma. So really what they're trying to do, and their goal is, as for-profit companies, maximize their investment and get the largest return on investment they possibly can. We're looking to turn this model on its head a little bit. One of the things in our vision is the FDA in the United States has a spectacularly great program called the Pediatric Priority Review Voucher Program. So for every gene therapy you get approved, you essentially get a check for $150 million. That makes a pretty good business plan for if you can get a gene therapy over the finish line, you get a $150 million check. You can use that to then bring more therapies over the finish line. So our goal is to actually bring gene therapies into the clinic, but using a public health lens approach instead of what the market will bear as far as maximum price approach. And so there's a team of us at Dalhousie University that's looking to leverage prior success that we've had in therapy development for kids, primarily using not-for-profits, grants, philanthropy, and venture philanthropy. So that way you have very limited exposure to venture capital and pharma, i.e. you can control the price out the other end. So we can have undiluted methods to bring gene therapies at a reasonable price versus what's the maximum price. So that's our goal, and we're quite certain we can do it. The other thing we're looking to do is, because these gene therapies are all very similar, one gene is broken. The gene therapy process enables us to platform this so we can plug and play different genes for different inherited diseases into the same gene therapy vector to really speed up the process and decrease the cost by which it takes to bring it into the clinic. So I'm going to talk to you about one example where we've had some success, but we're moving forward across several different gene therapies right now. And it's a rare form of a muscular dystrophy. And these kids basically have a defective gene called CHKB. So when this one gene doesn't work, you end up with an inherited muscular dystrophy. And for these kids who unfortunately get this one defective gene, the onset of disease is about 2 to 4 years. That's when they start to feel they can't hold their head up, they can't sit, they can't stand or walk. And patient survival for these kids is maybe early 20s before they pass away. Basically from muscle weakness, in the end their diaphragms can't go up and down and they can't breathe. There's absolutely no cure for CHKB disease. Basically management is physical therapy and occupational therapy. So again, tragic, but what we sought out to do was take our gene therapy platform that we've developed, and the first thing we had to do is, there's actually mice out there that are missing the exact same gene that kids are. And they actually get the exact same muscular dystrophy that children are. And of course, you can't go from a test tube into a child. You have to prove you can actually treat a model of the disease, often a mouse model of the disease. It's the reality. FDA makes you do it, Health Canada makes you do it, the European Medicine Agency makes you do it. It makes perfect sense. You also have to make sure it's safe, it's not toxic, all sorts of reasons you need to go there. And so this same mouse is missing the CHKB gene and it gets a muscular dystrophy. We took our gene therapy, we tried 3 different doses. The reason we tried 3 doses is our medium and high dose are what's currently used in the clinic to treat other muscular dystrophies. We tried those 2 doses, and then we went half of that. And I can say at the lowest dose, which is less than has ever been used in the clinic, we were able to treat the mice, and they worked just great. So that really increases our odds of this actually translating into being able to be used in kids, which made us very happy. I'm going to show you a bunch of pictures that aren't going to be super exciting. I find them super exciting, but hopefully I'm going to try and make them super exciting. But really, we treated the mice at 3 weeks of age when the disease is just starting in a mouse, which would be like a 12-year-old, 10-year-old kid. And we let it go for 6 weeks of age. And then we looked at the mice and said, how well do their muscles look and how well do their muscles function? Pretty straightforward. So this is looking at, is the gene present? In a normal mouse, the green cells here mean this is the gene being expressed, and you can see the gene is here. The knockout mouse, of course, the gene is missing, no green. And then when we actually use the gene therapy to try and put the human gene back into the mice, everything's green again. So voila, we can actually get the gene into the muscle cells of these mice. That's part one. Now, does it do anything? The second thing we had to do was, I know everybody wants to see a graph first thing in the morning, but basically this is a wild-type mouse, and that's how much its quadriceps weighs. The knockout mouse, you can see the quadriceps mass is already decreased to almost nothing. You put the gene therapy back in, the muscle mass is back to normal. So we can actually rescue all of the muscle and bring it back to a normal size when it's actually atrophied to next to nothing in the knockout mouse, and the same thing happens in the children. So, of course, we're hoping that what we see now in the mouse, we can translate to kids. Using the exact gene therapy that we've used for the mouse, we don't need to do much modifying. And this is just showing injury markers of muscles, and of course the injury markers go up when your muscle's injured. With the gene therapy, they're back down to normal again. So, looks great. If you actually, again, and I'm going to go through these a little bit quicker, but again, it's using our gene therapy. A wild-type mouse, this is a stain, different stain to look at muscle. The knockout mouse looks gross. I'm going to go with the scientific term, gross. But then when you put the gene therapy back in, again, everything is 100% normal. We've had pathologists look at this that are blinded to everything, and they've scored these, and that's what they see, and that's what they tell us. There's different types of muscle cells. I'm just going to go with, there's 3 kinds, and for the sake of this audience, I'm going to say there's purple, there's red, and there's green. And you can see in the knockout mouse, those go sideways. You put the gene therapy back in, and the 3 different types of muscles that are present in our skeletal muscle, again, 100% normal. So we're essentially curing this disease in our minds. And the terminal phenotype, this took a long time for us to figure out, well, why do these muscle cells die when you're missing this CHKB gene? They actually fill up with fat. Big globs of fat accumulate in the muscle cells over time. And in a normal muscle cell, you don't have any fat, which is good. These red dots are big globs of fat gobbing up the works in a muscle cell. And actually, when we treat with the gene therapy, these big globs of fat have disappeared as well. So we reversed everything we know about as far as this muscular dystrophy in the mouse model, which is almost an exact replica of the disease in kids. Makes us very happy. The last thing we wanted to do is, well, can their muscle cells actually work? So I don't know if anybody here has had a stress test where you have to run on a treadmill for a little while, or some people voluntarily choose to run on a treadmill for some reason. Well, if you put a mouse on a treadmill, it likes to actually run on the treadmill, so it'll run on the treadmill for as long as it feels like. The mice missing the gene, of course, they've got a muscular dystrophy, they really can't run on the treadmill all that long, and as you put the dose of the gene therapy back in, their movement is actually restored. So the muscle cells work as well. So all the things we know that go wrong with these muscle cells are 100% corrected by this gene therapy, and the muscle cells actually work, and the mice can run again. So, what are we trying to do? Our mission, and this is the team, there's myself, there's Mahtab Tavasoli. Mahtab was a postdoctoral fellow in my lab. She's now a professor at McGill University. These 3 other folks are very important. Eric Hoffman is newly 10 years ago transplanted into Nova Scotia. He's CEO of Agata Biosciences, which is in the old brewery market. It went from 4 people to 60 people. What Agata Biosciences does, it actually does the clinical trials for neuromuscular diseases for a lot of pharma folks and does all the analysis. So we've already got a built-in Halifax-based business that can help us with the back end. And what Eric and Jesse and Laura did with a company called Reveragen was they used just grants, philanthropy, and venture philanthropy to bring the first therapy for a different kind of muscular dystrophy called Duchenne's muscular dystrophy into the clinic and into the market using only 4 people and undiluted funding from grants and philanthropy. And their therapy is now in 50 countries, including Canada, and dramatically improves Duchenne's muscular dystrophy. We're working on a different muscular dystrophy using a gene therapy that we know can now cure the mouse model. And because they have the expertise in getting another therapy all the way through into clinical trials and out the other end and approved in over 50 countries, there are collaborators that are going to help us do the exact same thing with our gene therapy for our muscular dystrophy. The thing that's our business case is, okay, we've got one disease that I showed you as the thin edge of the wedge, the CHKB-mediated muscular dystrophy. There are thousands of inherited diseases, and we've got, because we specifically designed our gene therapy vector is what it's called, to be able to plug and play as many genes as you feel like, that we feel will now be able to treat many of these diseases the same way we can treat this mouse, and hopefully move on to the kids for all of these diseases. And the business case is pretty straightforward. Remember we said we don't want to actually maximize profit. We want to use a public health lens, i.e., can we bring these into the clinic at a reasonable price versus the maximum price? Well, for us, since this pediatric priority review vouchers are worth $150 million a pop, and it takes about $10 to $20 million to bring one of these gene therapies all the way through to the end. That's a pretty good return on investment that will enable you to recycle and bring more gene therapies to our platform. And once you platform it once, the regulatory process gets a lot easier to platform it the second time, the third time, the fourth time, so the speed and the cost goes down every time you do it. And so our plan is to do exactly that. Use our plug-and-play gene therapy process to try and bring in, using these PPRVs as a business case, as many of these gene therapies as we can possibly get through at any one time to treat as many kids with these different inherited diseases as possible. So that's what we're up to right now. So that's my time, and I'd like to thank you very much.
Thank you very much, Dr. McMaster. I'm clearly not that menacing when I'm approaching the stage there. So, please, we'll have a chance to bring all our panelists up at the end. If you have questions, we'll bring them up. So if you're thinking questions, hang on to them and we'll have a chance. So next I'd like to welcome Dr. Luke Chen. So Dr. Chen is unable to join us in person, but he has prepared a video. Some of you may have heard him last week on CBC. So Dr. Chen's work is helping us to fast-track new treatments for rare diseases through drug repurposing. That is, the drugs that we know are safe and are used for one thing can be used for something else. And Dr. Chen is a hematologist and professor in Dalhousie's Faculty of Medicine, and he's as well as an affiliate professor in the University of British Columbia. His clinical and research expertise focuses on rare inflammatory and hematological diseases, including cytokine storm syndromes, histocytic disorders, autoinflammatory diseases, IgG4 related diseases, and eosinophilic disorders. Hopefully, those are terms that no one's had the unfortune of being familiar with. He also serves as an international advisor to Every Cure and the Castleman Disease Collaborative Network, which recognizes him as its 2024 Physician of the Year Award. In addition, Dr. Chen directs the Coastal Rare Inflammatory Diseases Program and supports research, training, and care for patients living with rare inflammatory and blood disorders. So now we have a chance to see the video. So if you can turn your attention to the screen. I know I can't, the timing of this one will be impeccable. So there we go. Thank you very much.
Greetings from England. I wish I could be here with you in person today, but my name is Luke Chen. I'm a hematologist and professor of medicine at Dalhousie and an affiliate professor at the University of British Columbia. It's really a pleasure to be able to tell you a little bit about my program, the Coastal Rare Inflammatory Diseases Program, or CORID, where we work on repurposing drugs for rare inflammatory diseases. I'm from Nova Scotia, but I spent 17 years working and studying at the University of British Columbia, where I did research on a number of rare inflammatory blood diseases. And during that time, I became a resource for physicians dealing with these rare diseases from all across Canada and the United States. When I moved back to Dalhousie in 2023, I realized that I had a rare opportunity to build a national and international network to improve the clinical care, education, and research around these rare diseases, and thus the idea for CORID was born. One of the main problems we face in rare diseases is simply economic. There are over 18,000 known human diseases, but only 4,000 FDA-approved drugs. And so what can we do for those other 14,000 conditions that don't have their own drug? Traditional drug development is very expensive, what we call the vertical drug pipeline, taking a promising molecule from animal studies to clinical trials to FDA approval, costs about $1 billion and takes at least a decade to do. A more cost-effective and efficient way to find new treatments for rare diseases is what we call horizontal development or drug repurposing, which simply means taking a drug that's already been approved for another condition and testing it, using it in those rare diseases. One of the best success stories for drug repurposing in the past decade was led by my colleague and friend, Dr. David Feigenbaum at the University of Pennsylvania. David, these are pictures of him. He likes to joke that these would be the world's best before and after pictures if he could just flip them the other way around. You see, David was a quarterback at Georgetown University. He was a very fit, very strong Division I athlete. And then when he went to the University of Pennsylvania for medical school, he developed a very severe, very rare inflammatory blood condition called TAFRO. The known treatments for TAFRO at the time did not work very well for David. He had to undergo high-intensity chemotherapy. You can see he's lost all his hair there. And the treatments didn't work very long. They would put him into remission for a few months. The disease would come back, threatening to shut down his organs and take his life. So when he was sick, David studied his own blood, or collected his own blood, and when he was well, he studied it, and he realized that a drug called sirolimus, which we use for renal transplant patients, would likely also work in his condition. And so he repurposed sirolimus for the treatment of his own TAFRO, and it worked. He's been cured for the last 11 years. That's a picture of David with his wife, Caitlin, and their first child. He wrote a best-selling book called Chasing My Cure, which is being turned into a movie this year. And for me, one of the best things about moving from the West Coast to the East is that I'm much closer to collaborators like David at University of Pennsylvania. So David's latest organization or effort is called Every Cure, where they try to leverage the power of artificial intelligence or machine learning to repurpose drugs for rare diseases. And since my move to the East, I've been able to do a lot of those collaborations with him, and they've been very fruitful. Today, I'd like to share with you just one recent success story from that collaboration. This is a drug-disease pairing between lenalidomide, a cancer drug used in other hematology diseases, and a very rare disease called Rosai-Dorfman-Daytum disease. The story begins several years ago when I was still in Vancouver, and I was asked to give an opinion on a 54-year-old lady originally from India who had developed a mysterious skin, lymph node, and blood disease. And she'd seen numerous specialists with no diagnosis. No one knew what she had. She was sent to me, and after a careful review, I realized that she had this rare disease called Rosai-Dorfman-Daytum disease. This is a picture of her skin. She had these painful, itchy, uncomfortable nodules and plaques all over her face, her body, her hands, her feet, even on her palms and soles. And of course, it's wonderful to get a diagnosis, but we can't stop there. The most important thing is to get the person onto effective therapy. Unfortunately, the other barrier to Rosai-Dorfman-Daytum disease, aside from the difficulty in obtaining the diagnosis, is that the existing therapies don't always work. In fact, many of the existing therapies have response rates of less than 40%. So I tried several therapies for her, but none of them got her any better. Around that time, I was beginning to investigate this drug called lenalidomide, which we commonly use in another blood cancer called myeloma, which is much, much more common. And I realized that similar pathways were at work. So I gave her lenalidomide with a steroid called dexamethasone. And she was the third person in the world treated with that combination. I had treated the second person in the world a few months earlier and it worked. So I put her on it and it worked very well. Within a month, her skin felt much better. Before 2 years, she was completely cured of her disease. And so we were able to publish her case in a journal called New England Journal of Medicine Evidence. But the problem at that point is, how do we scale it up? We had, my research team and I had come across a disease drug pairing that we felt was very effective, but we weren't sure how to bring these results forward in a way that affected practical treatment guidelines. Around that time, the New Yorker magazine was interviewing Dr. Feigenbaum's team. This was last summer, July 2025. And what the New Yorker was interested in was how Dr. Feigenbaum's team at Evericure planned to use artificial intelligence to repurpose existing drugs for rare diseases. And their approach is very ambitious. They have what they call an all-v-all matrix, where they take all the world's information about every known disease and all the world's information about every known drug and plug it into the computer and see what it comes up with. So around the time that they were doing that interview, I was speaking to David about this disease drug combination, rosidorphin, datum, and lenalidomide. And so they interviewed me as well. And they said, well, this doctor in Canada, Dr. Luke Chen, is asking Evericure about this disease drug combination. And so they plugged it into the algorithm, and it scored very, very high. It scored in the top 0.3% of all drug disease matches. And so David and I decided to go ahead with that project. And so over the next year, one of my very bright young residents, Dr. Emily Leung at the University of British Columbia, worked hard to gather all my clinical experience with rosidorphin datum disease and compare it with, combine it with the computational data from Evericure. And she was able to publish that paper in early April in the American Journal of Hematology. And what we found is that in my experience over the past few years, I've treated 11 patients with rosidorphin datum disease, and 10 of them had an excellent response, including this man. You see a CT scan at the bottom left there of a large orbital mass that shrank down very nicely after a few months of lenalidomide and dexamethasone. And on the Evericure side, they looked at almost 3,000 drugs in rosidorphin datum disease, and they found that this combination that we had come across, lenalidomide and dexamethasone, scored among the very top disease drug pairings that they could examine. And so this publication has been brought forward to the National Cancer Care Network in the US, which is responsible for the guidelines for treatment of these rare blood disorders. And they're going to use our study to increase the prioritization of this disease drug combination so that other people from all around the world who look at these guidelines will be able to know about lenalidomide and dexamethasone as a safe and effective option for their patients. Importantly, many of the treatments that we use in rosidorphin datum are very expensive and only available in North America and Europe, whereas lenalidomide and dexamethasone is widely available even in low-income countries like the Philippines and South Africa. So this, we feel, is a very important success story from our collaboration with Evericure. In closing, I'll just say that I think this is just the tip of the iceberg. I only had time to present one story to you today, but there are so many more that we're working on with our collaborators in the US. And the beauty of it is that all we need from the Nova Scotia side is support for my research time and my residents and fellows research time, and then we're able to leverage all the resources of the large labs and large research groups that my collaborators in the United States and Europe have. So thank you for your time. I wish I could take questions in person, but if you have any questions, please feel free to email me.
That was great. I'm so glad that Dr. Chen had the opportunity to make that video for us. I think that's important and exciting work. So, and again, he would welcome questions if you had them. Now, please join me in welcoming Dr. Manuel Matiasen to the stage. Using genomics and advanced data science to uncover the genetic drivers of mental illness, Dr. Matiasen's work focuses on improving precision approaches to mental health diagnosis and treatment. Dr. Mathiasen is a physician and a scientist specializing in genetic epidemiology, biostatistics, bioinformatics, and molecular genetics. His work focuses on translating genetic discoveries into clinical diagnostics and mental health care through global collaborations across Asia, Africa, the Americas, and Europe. His lab investigates genetic risk factors, predictors of disease course and treatment response, patient-centered implementation challenges, and advances in quantitative methods. Across all areas, his research integrates phenomics, molecular genetics, and data science to drive precision medicine in mental health.
Thank you very much, Elaine.
I'll menace you later.
Okay, thank you so much for the opportunity to speak to you here. This is unfortunately for many families, a reality that they face. Maybe not this very specific case, maybe they don't want to have children, but they're facing it in a different way. And that is that at some point in life, they come up with the idea that members of their family are suffering / have mental illnesses, like, for example, depression, schizophrenia, or other fairly common. And you see here that we actually switch gears not to talk about rare diseases anymore, but to actually talk about fairly common disorders that sometimes up to half of the population actually encounter throughout their lifehood. And the other thing that's going to change is that we're not only talking about one gene that we have to target and therefore can happily look at a treatment that we could happily do in the other presentations that you saw, but they were looking at hundreds, sometimes thousands or 10,000s of genes that all in concert have very small effect on the disorders that we are talking about. So when I started med school, far too long ago, that was basically a question that people would ask. And our psychiatry courses still taught us that mental illnesses, well, it's not exactly known whether genetics actually plays any role in them. Schizophrenia, for example, my professor was very sure that genetics doesn't play a single role in that disorder. And it was, for example, in 2001, and many of you might recognize Dr. Francis Collins, later in his role also as the director of the National Institutes of Health in the US, also during the pandemic. And this statement or this testimony that he gave to the United States that for quite a long time, unfortunately, shaped the public eye on what genetic research has done for society and what it didn't do that was promised. And so this is almost to the day 25 years ago. And many of the predictions, especially the ones for later years, unfortunately didn't come through yet. So I'm not saying that they will not come through in the future. And amongst those was the prediction that by the year of 2020, the diagnosis and treatment of mental illnesses will be transformed. And while that's not entirely true, I think we made a lot of leeway actually to this prediction or to make this prediction true. And so maybe we are just delayed by a couple of years rather than that that's never going to happen. So how do we get there? Before Dr. Francis Collins made this statement already, there were studies out there looking into so-called family studies, looking into twins and those where both twins were actually sharing the same genetic background compared to those where they don't, so monozygotic, azygotic twins, to see how much just genetics actually play a role in these illnesses. And for many of them, schizophrenia, bipolar on the top, there's a very high contribution that genetics actually does. So there's a term called heritability that we use in genetics, and schizophrenia, bipolar estimates at the time were that 80% of the variation in the disease picture that you see are actually due to genetic causes or genetic factors that play a role here. It's lower for other disorders. Depression, it was around 40–50%, but you get the picture. So people were really enthusiastic, starting to do genetic studies with the money that they had at the time. It was still expensive. Technology wasn't there. And that led to a phase where so-called genome-wide association studies where you compare parts of the population, one part that has the disorders, the other part that doesn't have the disorder, against each other to see whether you can identify a genetic signal, that those studies basically failed. We did that for a long time. I keep saying they, I was part of the culprits, so we did it all together. It was not very successful, but we realized soon that that was not the case because the approach didn't work. It was just the case because people didn't work together. And so around the early 2000s, something happened in the field where people stopped fighting each other over publications, over research money, and so on. Not that we don't do that still, but at least not to the degree. And they came together, formed a huge, large-scale consortium called the Psychiatric Genomics Consortium, which by now has a couple of thousand researchers actually joining them, and to pool their data, come together, work together, and identify for the first time genetic loci that make you more likely to develop psychiatric illnesses, including schizophrenia. The paper here depicted in the lower right panel is the one for schizophrenia. It's a study in 2015 that we had the leading part in. And so for the first time, we really identified hundreds of genes that were part of the disease etiology for a disorder like schizophrenia. Unlike the cases that you have heard so far, having any one of these genes doesn't make you very likely to develop schizophrenia. It's a combination of many of these genes that all have very tiny kind of effects by means of changing how much of a certain protein you express in your genes and so on, that actually makes it likely. Following this success story, everybody else was kind of like, yes, that's what we have to do. So it wasn't only schizophrenia, bipolar was basically next. Depression took a little bit longer, but we'll see that they also got there. And so we are now turning more towards what the future might be, and not 2020, but maybe 2030, where we can go into, okay, what do we know now from all the genes that we have identified, and how do we translate that into care and into new treatments? And when people think of genetic results, there is usually this conception that, well, there must be then a cure and we change something in the genes and this kind of works. But it's not exactly how it works for so-called complex disorders like mental illnesses. It's more likely that through these massive combined efforts, and you can see here that we are by now talking about millions of people in terms of participants in our studies that come together to help us identify genome-wide significant hits. So coming from this drought era of kind of GWASs that didn't really show something, we are now somewhere where basically every major mental illness has identified genetic signals that predisposition people to develop them. And not only that, we can use these results to actually understand more of the relationship of these individual disorders to each other. So for example, why is it that schizophrenia and bipolar disorder not only clinically look so similar in parts of what they are, but that there's also a common genetic basis actually to these disorders. The very common story here really is that the more participants you have in your studies, the more likely you are to be successful. The only problem with that is that the traditional approach to go to hospitals to ask patients whether they can participate in studies doesn't work anymore because that will not get us the numbers and is far too expensive to actually do. So the more likely scenario is that you use existing resources that have been done on a population scale usually and use the information that these resources can provide. One example is the UK Biobank, for example, with 500,000 participants and a very broad set of information that is available. Other examples are FinGen, Finnish study, and so on and so on. So where are we now in 2020? We are at the beginning of getting there what Dr. Francis Collins promised. There are different areas where we can actually make a change. One is prediction of response, for example, in bipolar disorder, predicting which of the patients will respond to lithium treatment or not. Same goes for depression and SSRIs. We are at a stage where we can do early intervention strategies, so we identify those at risk for disorders like anxiety disorders, for example, that happen in youth, so that they don't go on actually to have diseases. And all that is made possible by something which is called polygenic risk scores, which is just a summation of your risk that you have based on your genetic information and how much that actually makes you more likely to have a disorder or not. Unfortunately, we are not talking about treatment here. We are really more talking about intervention, prevention, early identification. But we still believe that this will help us, and the successful collaborations that we have, to actually get the ever-rising numbers of mental illnesses or occurrence of mental illness actually down and help those that actually are affected to get identified at such an early stage that treatment is possible, the treatment that we already know, and that will make their lives better in the end. Thank you very much.
Thank you very much, Dr. Matheson. Our final speaker today is Dr. Sanja Stanijevic, who will speak to her research on data-driven genomics data approaches to improving respiratory outcomes. Using large data sets, her work helps build stronger, evidence-based tools that support better patient care. Dr. Stanijevic and her lab study how lungs grow and change throughout the lifespan, generating important insights that continue to strengthen our understanding of respiratory health. She also works to translate these findings into practical, real-world approaches that clinicians can use in their everyday practice, ultimately helping improve the accuracy and effectiveness of lung disease assessment. Dr. Stanijevic recently led, with a great deal of effort, with team members, the development and launch of the Nova Scotia Lung Wellness Clinic, which was so generously supported by GSK and the Lung Association of Nova Scotia and PEI. This new clinic helps tackle the long wait list for lung testing in Atlantic Canada, while also contributing to regional research. So welcome, Dr. Stanijevic.
Good morning. Thank you so much for being here this morning. I'm going to switch gears a little bit. I'm going to tell you about a condition called cystic fibrosis. And I think this is a really powerful story because it highlights what you've heard today, the impact that has on people's lives. And I'll share the story of what we do here at Dalhousie to contribute to the success in changing people's lives. So cystic fibrosis is one of those rare genetic diseases that Dr. McMaster told you about. One tiny error in the genetic code causes the misfolding of the CFTR protein. Because this protein is found all across the body, people with cystic fibrosis struggle to do the things that we take for granted every day, digesting our food, breathing, and everyday behaviors that we come to do. A few years ago, 3 tiny little molecules that were discovered in the lab through the science that you've heard about today have transformed the lives of people living with cystic fibrosis. This is CF. Prior to this therapy that was developed, people with cystic fibrosis would have been expected to live to age 25. When the gene was discovered, half of babies died long before they reached adulthood. The disease required daily intensive therapies, 2 to 4 hours of daily physical therapy, inhaled therapies, a myriad of pills that they had to take every day just to function and do the things that we take for granted. With the advent of the science and the 3 little tiny molecules that improve outcomes, today people with cystic fibrosis are not just surviving, they're thriving. Based on our modeling, we can expect that babies born today can live beyond 65 years and live very good, high-quality lives in that time. So let me tell you a story about how we contributed to getting these therapies here in Canada. You've heard about Francis Collins. This is him on stage at one of our premier cystic fibrosis conferences in 2019 when the FDA approved Trikafta, these 3 tiny molecules. So Dr. Collins stood on stage playing his guitar, celebrating, telling the audience that these families can now dare to dream again. In Canada, we waited. Because of our cumbersome policies for approving rare disease therapies, because there's only 4,875 people with cystic fibrosis in Canada, we could not get these life-saving therapies into the hands of Canadians. So at Dalhousie, we partnered with the community. We partnered with people living with Cystic Fibrosis Canada, the non-for-profit patient organization, and we used data to inform the Canadian government on what they were missing, what impact there would be on the Canadians living with cystic fibrosis if we didn't get access to these therapies. Now, CF, because it's very common and has been around and we've known about it for over 70 years, we had marvelous data. Since the 1970s, every patient, every person with cystic fibrosis in Canada, from their first breath and their diagnosis to when they died, we've kept meticulous records of every clinic visit, every medication they've been on, every hospitalization, and we were able to leverage this data to understand what would happen if we applied what we knew about these therapies to the Canadian population, and what would happen if Canada waited. What would happen if we waited just 5 years? And the results were compelling. We saw that we would reduce 15% of all deaths that would occur in the next 10 years. We would reduce hospitalizations by 60%, and most importantly, we would improve the lives of those individuals. We estimated a survival gap of 9 years. So just by waiting 5 years for this therapy, we could prevent or improve life by almost 10 years. This evidence that we generated together with Cystic Fibrosis Canada led to one of the most effective advocacy campaigns. We had over 8,000 letters written to MPs and regulators, and this was part of the evidence that was used to convince our Canadian regulators that this drug was effective. Well, we knew that from the clinical trials, but that it was valuable to Canadians, that it was worth investing in these very effective but very expensive therapies because they would improve the lives of Canadians. We didn't stop there. We worked together again with our patient partners, looking at the burden of disease study. One of the reasons why it's so hard to fund rare diseases is because most of our regulatory pathways are designed for blockbuster cardiovascular drugs, the kinds of conditions that many people have. We don't have the right tools and resources to evaluate the impact of these therapies, these very expensive but very effective therapies for rare diseases. So in our burden of disease study, we surveyed and looked at Canadians and understood, what does it mean to live with cystic fibrosis? What does it mean for the families that have to miss work, that have to sit in hospital, that have to take lesser jobs? What does it mean for those hours of therapy, 4 hours a day, that those families could be doing something else? And we quantified the burden of cystic fibrosis. We quantified how much economic value is saved by having access to these therapies, which led to further approvals and more access to even more innovative therapies that now exist. Ooh, I'm gonna go back one. But we're not done. While we have these new therapies for most people living with cystic fibrosis, there are very rare indications, and as you heard from Dr. McMaster, there are thousands of rare diseases. So here at DAL, we're innovating how we conduct clinical trials, how we look at one therapy for many diseases, called umbrella trials, or we looked at many therapies for different conditions. We looking at in vitro or cell-based studies to understand whether these therapies will work before we go into clinical trials. And we're understanding how we can conduct clinical trials more effectively to be able to get these therapies into the hands of Canadians sooner. We're also innovating how we measure lung health. These therapies are transformative. All of the tools that we've used to date to monitor and track how these medications work, to track disease progression, no longer work because people are so healthy. And so we're innovating imaging techniques that allow us to visualize exactly how air moves through the lungs, where disease is, and how we can improve outcomes. We're looking at measuring lung function in children as young as 2 years of age so that we can identify early disease, intervene before lung damage is permanent. Most importantly, we're training the next generation of data scientists. We've amassed huge amounts of data, and without the trainees, without the expertise to gain insights into this data, we aren't going to move further. Dalhousie is the lead for the Atlantic Stage program, where we're training Atlantic Canadian trainees in genomics and genomic epidemiology. These trainees have access to national and global world-class resources and funding now to be able to get trained by the best and brightest in the world. And I'll just close because Eileen's at the stairs. I love what I do. Every day I get to see the impact. I get to see how our research changes the lives of Canadians. And this is Sebastian and his mum, and I'm really pleased that the work that we do here at Dalhousie has allowed them to be able to dream again too. Thank you so much.
Oh, thank you so much, Dr. Stanievich. So that concludes our presentation portion of the morning. Before we continue, please join me in thanking all of our researchers today who shared their stories and their research and their passion with us. As you have heard through today's presentations, genetics and genomics research is opening new possibilities for earlier diagnoses, more precise treatments, and better health outcomes for patients and families. These discoveries are made possible through a combination of public funding, institutional support, and philanthropy. While traditional research funding remains essential, philanthropic support often provides the flexibility needed to pursue bold ideas, generate early evidence, attract additional funding, and accelerate promising discoveries from the laboratory to the people who need them most. To the many supporters and friends of Dalhousie in the room today, and I thank you all for your past and support in many ways, thank you. Your generosity helps create the conditions for innovation and breakthrough discoveries. The impact of philanthropy can be found beneath many of the advances that we're celebrating today. So thank you to everyone. So if today's discussions have sparked your interest and you would like to learn more about the research underway at Dalhousie or the ways we can help advance it, members of the advancement team would be pleased to speak to you following the event. Thank you for being part of this important conversation. Also, let's celebrate our collaboration. Everybody's story today, all those researchers talked about how we're leveraging things by working better together, and that's one thing that we do well here. And today's events like this show that as well. You're our partners as well. So we'd now like to invite unfortunately Dr. Chen isn't here, but we'd like to invite the other presenters to come back on stage for a Q&A panel. This is an opportunity to delve deeper into the topics discussed. You can quiz them like a thesis defense if you would like, with those probing questions. So as the speakers return to the stage, I would like to draw your attention to a few things. First, please check out our Remedy magazine available throughout the room. It features stories about medical and health research and education across all of Dalhousie's medical campuses. Our next issue is coming out, I think in the next few days. So if you would like to receive this magazine in the mail, please let one of our advancement staff or the registration table know. So now we've got a few minutes and we've got people on stage. So I welcome any of your questions from the audience. This is always the part. Oh, great, please. I'm just going to repeat that just quickly, if that's okay, Manuel, just in case anybody couldn't hear it. So we had a great question from the audience about how this work can help inform diagnosis so that people can be diagnosed perhaps earlier and more accurately because it's a challenging thing for the clinicians to do and there's no shortage of unmet needs. So please.
Yeah, it's actually a very good question, and part of the research for a very long time has actually focused to shift away from what classic DSM-5, ICD-11 or so criteria are towards biomarkers, which genetics is just one of them. You could look into molecules or other things. And I think, unfortunately, we're not there to kind of completely change how we diagnose mental illnesses, but I think we can inform ICD-10, ICD-11, DSM-5. So for example, OCD no longer is an anxiety disorder based on DSM-5. And I think part of that has been because of biological evidence, including genetic evidence, how these disorders kind of fit together, but also don't fit together to some degree. Another example is for a very long time, ADHD and autism were exclusive kind of diagnoses where you couldn't give them at the same time. But we have, for example, done a study that individuals that have been diagnosed with both over the lifetime, that they share genetic risk both for ADHD and for autism. So you can use genetic information, I guess, to make changes to how the system kind of works. That's one thing. The other thing, I guess, is that genetics is information that you have at birth. That doesn't change, basically. There are parts to genetics, epigenetics and stuff that might be changing due to lifestyle choices and so on, but it doesn't change. And that genetic information is valuable information that you get from the get-go. And while that information might be less important over time, specifically when you start to come into an age where you are beyond the onset age that you would expect for a disorder, this information always can supplement what you actually know in terms of symptoms, what you know about how to diagnose, and to become part of something what we would call a multimodal model or risk prediction model that can help you to identify whether somebody is at risk for a diagnosis and can help supplement kind of how you diagnose.
Thank you very much. Do we have any other questions? Please.
My name is Michael Herrick. I have a new GP. He's...
Congratulations.
my other one retired. He was great. But first question I asked my GP was how old he was. He was 47. I hope he's not here. My question is, how actively are you communicating this information that you gave us to a 50-year-old GP who will perhaps make the initial diagnosis and a referral? How is this getting to them, to me, through them?
So let me start with saying that GPs are the most likely first contact actually with a mental disorder. I think 50% of all visits to a GP, one way or another, actually have to do with mental illnesses or mental health, let's put it positive. We do outreach, so we try to invite people to kind of learn about that, but at the very end of the day, we obviously also rely on them being interested. And so while common education or CME in the kind of medical field is something that is required, all or many of the conferences that we do actually include parts where these CME points for physicians actually are part and where they're invited actually to come there. Large-scale conferences like the IOCDF, which are organized by patient organizations, for example for OCD in the US, where treating GPs and physicians in general are actually invited to get educated. We talk a lot with those in the medical genetics field, how we can actually help them to help patients through counseling and then bring it back basically through the patients kind of to doctors. So there are, I think, many approaches that we try to use to inform them.
And I can say on the childhood front, where many of the diseases are inherited, what they're doing now is they're actually using AI, which is great, to scan medical records, because a lot of these kids, because you've got a genetic defect from birth, they tend to be frequent flyers of the medical system. They need to see many specialists. And before genomics and genetics came along, it took about 7 years and $20,000, $30,000, about 5-6 different specialist visits, 2 to 3 different misdiagnoses before you got diagnosed. Now that we can sequence genomes and we can use AI to find the frequent flyers of very young children who are almost always rare disease kids, we can pull them out right away, sequence their genomes, and find these kids within weeks or months for far less money, and also know the gene that's defective that causes their rare disease, where before it took 7 years to get a clinical diagnosis, and then you might get a genome done and find out your gene. So on the children's side, there have been big strides, and the GP even doesn't need to know, because the AI is actually yanking it out of the medical records and then circling it back to them to let them know exactly what's wrong with the child.
Thank you. We've got another question over here, and Emily, if you can bring the mic.
Hi, good morning, and thank you very much. My question is about CF, and it wasn't clear to me when you talked about the approval in Canada for trifecta. I'm assuming it's approved now. But my question is, how soon do you start that treatment with a diagnosis, and does it change over time as the person ages?
Yeah, absolutely. So the Trikafta is approved in Canada, as are some of the newer versions of the same medication. And what's really remarkable about the CF community is we've been able to do clinical trials in children as young as 1 year of age. And if we initiate therapies at early in the diagnosis, we have newborn screening that identifies children at birth. And then if we can start these therapies before permanent lung damage starts, they basically have the lungs and the bodies of an otherwise healthy individual. And now we're more worried about the side effects and the long-term consequences of these therapies. If somebody started Trikafta later on in their disease course where the lung damage and organ damage was already permanent, then what we are able to show is they're maintaining at where they are. So they still have complications of their cystic fibrosis because it's been advanced and progressed. But it's remarkable because if we can get these therapies started at the time of diagnosis, these children lead otherwise healthy lives that are not impacted with CF at all.
Excellent symposium. My question is primarily for Dr. McMaster. Chris, as you know, a very exciting development in the last year has been CRISPR-Cas9 prime editing, basically correcting a nucleotide error in a specific gene, in a specific location. Seemingly cured a patient with chronic granulomatous disease, the type of patients I, as an immunologist, looked after since the late 1970s here at the IWK. And the issue there, that Elie Haddad at Saint-Justine and Stuart Turvey at UBC collaborated with a private company to bring that about. Now, I think one of the issues was the company has stopped producing the CRISPR-Cas9 construct. And so I've had this kind of thing happen before, too, where I couldn't get therapy for a patient where, you know, in 30 other patients it was found to be effective through, you know, university clinical collaboration. Then the university privatized the vector, for example, and the private company wasn't getting its act together, and you have a child with severe combined immune deficiency waiting for the private company to get its act together, get approvals and all this. I mean, it's incredibly frustrating as a clinician,
Sure would be. Yep.
not to mention as a parent.
Yep.
Do you see any solution to this logjam in the bureaucracy and the profit-driven agenda?
You know I do, and I think what we're trying to imagine in terms of the approach we're taking, of course, is most of these companies end up with VC financing, there's some pharma financing, and they're having to get maximum return on investment. And when that investment is not returning enough money to those companies, then they tend to wind down these programs, despite the fact that they could have significant benefits for these children. The approach we're taking is a public health lens instead. We're a silly company in that we're trying not to make much money. What we're trying to do is use the $150 million pediatric priority review vouchers you get from the FDA that you get if you get one therapy over the finish line. It costs about $20 million to get your first therapy over the finish line. You'll have $130 million to then put back into, let's get the next one over the finish line. And we're trying to price it at as lowest a price point as possible. And the Canadian government's invested a lot of money in making gene therapy GMP labs available to Canadians in academic centers so they can actually produce the gene therapies at a reasonable cost. So that's the other thing we're trying to tie in right now with what we're up to, is this large investment that Canada's made in gene therapy production that's run by the government, that's actually meant to use, again, almost a whole of government approach to bring these therapies in at a reasonable price versus maximum price. And I think if we bring the price point in at a reasonable place, we're not going to run into approval delays because it's a lower price point. And the second thing is, because we're not trying to price it through the roof, everybody's going to approve it nationally. It'll make it a much lower bar, because that's one of the issues they have a lot of times, is the high price point. Is it really worth it? We're going to get rid of that barrier. The fact that we're plugging and playing into the same vector enables us to platform it, also decrease cost. And so the approach we're trying to bring is sort of a public health lens versus what the market will bear lens, and completely run it with the business plan of the pediatric priority review vouchers. You can then turn back into yet more therapies to bring into kids. And the $130 million you get will enable you to keep making the gene therapy over time, so you don't have to worry about it. So you can parse some of that to the side so that you won't run out of therapy ever. And so that's sort of the model we're trying to run with, so that we can not run into the problems that when you get it into the private sector, where they're trying to maximize profit, and it starts to not look like it's worth it anymore, they're just going to kill it. So we're trying to flip it around and take more of a grantsmanship philanthropy, venture philanthropy approach with the FDA's program as sort of the business model to enable us to keep constantly cranking these things out at a price point that's not going to be foolish.
Thank you. I think that the presenters will stay around for a little bit, but I've been charged with making sure we stay on time. So it's time to wrap up our morning and get all of you back to your busy days. So let's give our speakers just another round of applause. And thank you again to our sponsors, our gold sponsor, Shanex, and our silver sponsor, Dalhousie's Department of Medicine. Thanks to all of you for your presence and support today. Donors are crucial in research that directly addresses our biggest regional challenges. So please enjoy the rest of your day, and I'm sure if you've got more questions, these guys will hang around a bit, and we can always be contacted to find direct connections if you would like us to connect you. Thank you.